many physical problems can be modeled in terms of mathematics. Okay, and then it come to as a mathematician, we have to solve that problems. So there are many mathematical models which is coming from physical phenomena that give rise to the ordinary differential and partial differential equations, along with the boundary conditions and initial conditions. When it comes to mathematical equation, then we study about the existence and uniqueness of the solution. But many times it's happened that even we talk about there exists some solution, it is always difficult to find the explicit form of the solution. So at that time, then we have option that we can go and use some numerical method and try to find not explicit solution, but some approximate solution to the exact solution. Now, finite element method is one of the method here which will give the numerical approximation solution to ordinary differential equation or partial differential equation. And this finite element method is well studied and well established technique for the engineers. But, additionally, it has a rigorous mathematical foundation, and that mathematical foundation has started developing from the work of Professor Babuska Aziz from 1972 and Stan Fix. So what kind of questions we try to answer in this analysis, finite element analysis? The main objective here to obtain the reliable control of the total error. The total error means that error can be occur from the data measurement, or error can be coming from the modeling, from numerical approximation and computation. And also we have to give some algorithm such that we have to find out this optimal error control using efficient use of our computational resources. So now after this introduction, I will go to my main problem where I have worked here. I worked on the second order general elliptic equations. So I will introduce this problem and then I will give a little bit introduction to finite element method. And after that, I will motivate why adaptive finite element method is necessary. And I will give some algorithm by which adaptive finite element method works. And for this method, we will see how convergence analysis and quasi-optimality analysis has been proved. And in the last session, we will see the numerical experiment. So first, we will see the general second order elliptic PD. So general second order elliptic PD has this form: minus divergence of A gradient U plus UB plus gamma U equal to F. This is over some domain, bounded domain omega, and U equal to 0 over the bond. So basically this equation has a reaction term, convection term, and this is nothing but the diffusion term. So we are going to study the finite element method for this kind of problem, and finite element method is depend on the variational formulation, that also known as a weak formulation. So for the weak form of this equation is nothing but we have to find the solution U, which belongs to the Sobolev space H10 omega. So basically this H10 omega space is nothing but the here element which belongs to L2, and their partial derivatives are also belongs to L2, and function is 0 on the boundary. So how we get this weak formulation? We multiply with the test function V from the H10 omega to the original problem, and then we take the integration, and we use integration by part formula such that we try to shift this derivative over the test function. So by this way, we get this bilinear form, and that is A gradient U plus UB and gradient V gamma U V equal to FT. So here these are the assumption on the coefficient. A is the positive definite matrix, B and gamma are the bounded function, and given right hand side function F is L2. So now if we directly apply so basically our problem is you have to find U belongs to H10 omega that satisfy this weak formulation. But what happened in many application, we are interested in the solution U, but also sometimes we are interested in the flux of a flux variable. That means, for example, here the flux variable is P minus P is equal to A gradient U UB. So here at a time we want the good approximation for the displacement and also flux. And if we just go with the standard finite element method, then we will get good approximation for the displacement U. And then to find the flux, we have to take the differentiation of U. And suppose here we have some approximation like a piecewise linear approximation, and if you take gradient U, then it will give suboptimal convergence rate. So if we want good approximation for the main variable u and also for the flux, then we have to use the mixed formulation, mixed finite element method. To get mixed formulation, we will use this equation P is equal to A gradient U plus UB with minus sign, and try to write our original system in terms of first order system. And now we will select the space using these two equation. We will try to write the mixed formulation, and our mixed formulation will be, we have to find two variable, that is one is flux P and one is flux displacement U. And that we will take, we will use this first order ODE. We will select the appropriate test function, and we'll, again here we will use the integration by parts. So here in the for flux P, if you see this weak formulation carefully, then here we need the L2 inner product of the P variable, and also we need the divergence P. So for P, we have to first of all select the admissible spaces for the variable P and U. So here we will select the P from the H10 omega, because sorry, H div omega. Here we need the this P belongs to L2, and also we need the divergence P belongs to L2. So we will search P from the H2 omega, and U, if you see the U is just coming once with the inner product without its higher derivative. So we will select the U from the L2. So basically this is a mixed formulation we use when we want a good approximation for the main variable and for the flux variable. Now question is to find the numerical approximation to this one, and specifically finite element method. So how finite element method works? So generally, whenever we have to solve some problem over some domain. So suppose here I am taking the domain that is square domain 0, 1 cross by 0, 1 domain. So what we will do, we will divide this domain in the regular triangulation. So here you can see some triangulation is one triangulation is there, and over that triangulation, here each triangle is known as a element. Okay, and here we can see finite number of elements are there, and over this triangulation we will define the some space VH. And now here we are defining space VH such that V belongs to H10 omega, and here over each when we restrict this element over each one specific triangle, it will just piecewise linear. Okay, and when we have to find the solution, what we will do, we will define some basis function over the nodes. So basically this is, if you just see the vertices of the triangle are nothing but the nodes, and over that node we will define some finite basis function. So we will have finite basis function. So you can write your discrete solution as a linear combination of basis function, and the function which is belong to space VH, we will have such kind of form. So if you see, these are the continuous function, and over each triangle they are piecewise linear. So as I said, in the mixed formulation, we want approximation for the two variable P and U. So we have to select two discrete spaces, and such that it has some connectivity between two spaces. So for that, for flux, we are going to select the lowest order Ravier-Thomas space, which is subspace of H div omega. And here you these elements over the triangle has this form. It is again, if you see, it is a vector quantity, and it is a linear function. There is P0 plus P0x. It is a linear function, but it is a subspace of divergence or divergence space, and that is coming from the continuity of normal component along the edges. And the second space, we want the subspace of L2 omega. So for that, we have just selected piecewise continuous space. Okay, if you see, for over each element, this over each triangle function will be constant. So using this space and our mixed formulation, we will get new discrete formulation. Okay, and now our main task will be to solve this discrete formulation. So now our mixed finite element formulation is to find PM and UM such that it belongs to RT0 and P0. Okay, so now whenever we are coming with some finite element formulation, then there is a main question asked. First question is the whether our discrete formulation is well posed. Okay, and second problem is if it is well posed, if it is giving some solution, and is that so as h tends to 0. So here h is nothing but the mesh size of the triangle T. So if for triangle T, you can just take the longest edge and say h. And if you are refining it, if as h tends to 0, is your solution really discrete solution is approaching to the exact solution? And if yes, then what will be the convergence rate? So for the well posedness of problem, we have shown that discrete problem is well posed under the assumption that if our mesh size is sufficiently small, and for that we have used a tool that are non-conforming FEM and Marini identity. So this work has been in this article. So well-posedness problem is okay, but next is the convergence, and with what rate? So whenever we have to show the discrete solution is approaching to the exact solution, we have to do the a priori analysis. So for this problem, we have done a priori analysis, and the results are the for sufficiently small mesh size H, with this regularity assumption, 1 plus delta omega, and if u has this regularity, then we will have this kind of convergence rate. For u variable, it is h raised to minimum of 1 to delta. For p variable, the convergence rate will be h raised to delta. So what it means? So it means that if you have initial triangulation, so here suppose for this longest edge is the this one. So for this triangle, h mesh size is 0.5, and if you refine it, so as we refine, we expect that our and for refined triangulation, when we will solve the problem, we expect our discrete solution should be better. So here, this a priori analysis will make sure that your p minus ph, this error is bounded by h raised to delta. So here h is decreasing. So since h is decreasing, then clearly this error will tend to 0. So here is the graph. If you h is decreasing, then your error and error will be decreased. So it is make sure that your discrete solution is converging to the exact solution. Now next question will be, what is the convergence rate? So here convergence rate will be depend on the regularity. If your solution has regularity 1 plus delta, then for a flux variable we will have the convergence rate is only h raised to delta. Okay, so for example, if we are using piecewise linear and here we have only 1 plus delta, then it kind of suboptimal convergence rate. But if you do the a priori uniform refinement, we can get that much. But there are many problems. Like as if you have the convex kind of domain, your function is smooth, then we can get optimal convergence rate. But suppose we have L-shaped kind of domain, or suppose you have the solution which has a layer inside the domain. This layer is very sharp, and if you are approximating such kind of function with the P1 polynomial, obviously this will not give the good approximation at the on this interior layer. And to get good approximation, we have to refine this mesh very refine too much. So here specifically in this L-shaped domain, when this function has less regularity, that is 1 plus delta, and delta is strictly between 0 and 1, we will get only h raised to delta convergence rate. While in the smooth case, we get h raised to 1. Okay. Now question is, even if we have the less regularity, okay, even we have less regularity, can we get the optimal convergence rate, that is h raised to 1? This is first question. And even suppose your function is smooth, still can we do some refinement such that we can reduce our computational cost, because to capture this layer, if we need very fine refinement to capture this layer. So can we reduce this computational cost? Okay, so and here if you observe in the finite element method, generally when we refine the mesh, we get every time we solve the problem and we get new solution, and for that we are not using the previous level solution. And question is, can we use that previous level solution also? Then answer for all this question is the adaptive finite element method. So here we want to get optimal convergence rate even with the less regularity, and we also want to reduce the computational cost. So what is the adaptive finite element method? So in adaptive finite element method, what we'll do, if the function has singularity, then we'll try to identify that singularity, and we want to refine that particular region and get the good convergence rate. So here it is interior layer. We just want to identify that layer, and we just want to put our main target refinement over the singularity region or critical region. And if we do that, then we will get this kind we will get the optimal convergence rate instead of suboptimal convergence rate we are getting in the uniform refinement. But now main question will be here to identify where the function has singularity. It is difficult because the exact solution is unknown. We cannot find we don't know the exact solution, then how to identify this critical area. So for that, we have to go for the adaptive algorithm, so which will help us to identify this critical area where to refine. So adaptive algorithm contains 4 steps, that is solve, estimate, mark, and refine. And we have to use this loop again and again. So we'll start with some initial mesh. Suppose we are considering one sample problem which has a L-shaped domain. Here we consider initial mesh. Over that initial mesh, we will solve our discrete problem. After solving discrete problem, we will get this solution UM and PM. Now, we want our main target is after getting solution, use this solution and identify the area where error is large, so that we can just refine that area. That is our target. So for that, we have to find one estimate. We have to find the triangle where the error is large. So that important work has been done in the estimate state. So here we want to identify the triangle where the error is large, but to find out the error, we need the exact solution which is unknown. So for that, we have to find the estimator function, which is exactly equivalent to the error. But estimator has a property that estimator can be computed using only given data f and the discrete solution and PM. So for particular problem, we have considering the error in terms of P, H2 norm and L2 norm of U. And for that, we got this estimator. Now this estimator, so here error is bounded by the estimator, and this estimator has this form. So in this form, if you see all the quantities here are the computable. Either there is f, that is given function, ft is its projection over the mesh, and these all are the and PM are the given data. But having only one-sided bound, that is error is bounded by estimator, our target is to find out the triangle where error is large. So even estimator, if it is estimator is large, it is not saying that error is large in particular triangle. For that, we need the efficiency. And efficiency will take that guarantee that if efficiency we have to show estimator is bounded by error. And this will take the guarantee that error and estimator are equal. So whenever estimator is large, that's mean error is large. So what we do, so we will use the Doppler marking criteria. We will go to each triangle, and over each triangle we will find the estimator, and we will find the estimator. Suppose this is a triangulation, and the height of the triangle denote the amount of estimator. Then you can see this is four triangles has, or these two triangles has high estimator, and estimator is large. That's mean error is large in these two triangles. So we need to refine these two triangles. So we will mark this true triangle which we want to refine, and then we will apply our refinement algorithm. So so here these two triangles are get refined, and to make conformity of the mesh, we have to refine the neighboring triangle. So by this way, we get the another triangulation, and we will now apply the again our go to the solve state, and we apply the loop solve estimate mark refine again and again. So at the end, what will happen after applying this loop again and again, this our estimator will locate where the exactly singularity is. So here it is happening the singularity at origin. So so after locating this estimate, locate that is singularity, here estimator is large. So we marked and refine it. And so what is the effect of it? We get the optimal convergence state, which we are not able to get using the uniform refinement. So now, so numerically we can see it is working. But next question is, can we prove it theoretically? Can we prove the convergence of this algorithm? And can we show that this rate, whatever we are getting from the adaptive algorithm, is it's optimal? So if you recall in the a priori estimate, so a priori estimate to prove the convergence, what we have done? We have done u minus vh is bounded by h raised to tilde, some delta. And h is the mesh size of the triangle. And in uniform refinement, h is going to 0 because we are uniformly refining it. But if you see such kind of adaptive mesh, there is no guarantee that your h will tend to 0, because if you see here, h we are not refining more. So for several steps, here h is not going 0. But here, h is really going to small. So for that, whatever we have done in a priori analysis to prove the convergence, that method is not going to work here. So we have to think something else. Instead of mesh size, now we will try to do our analysis in terms of number of degree of freedom. So indirectly, for example, we can consider total number of nodes over the triangulation. So we have to prove that convergence using in terms of number of degree of freedom. That is total number of unknown over the discrete formulation. So now how to prove this convergence of adaptive algorithm. So what we do, to prove the convergence, what we have to do whenever we solve our problem from one mesh to another mesh. Okay, so this is first mesh, and that is solution is at this level. Solution is this mesh is 12. This is a discrete solution, and this is a estimator. And we refine. We go for the second. After refinement, we get to another mesh, and over that we get this kind of discrete solution. To prove the convergence, we have to prove that when we refine the error, mesh, so this is the refined one, and at this mesh, when you find the error, okay, at this mesh, when you find the error, it has a contraction property. That means there exists some alpha which is between 0 and 1, and contraction number is between 0 and 1, such that it is this error at the refined level is bounded by alpha time error at the PL level. So at each level, we have to show that your error is reducing. And for the alpha is between 0 and 1. And if it happen, if it's true, then obviously we can use this result recursively. And for in general, we can get that this total error is bounded by alpha raised to L, and alpha is 0 to 1, and this L denote the number of iteration. So this number will tend to 0, and we will get the convergence thing. Okay. Okay, I will try to finish as soon as possible. I think 5 minutes are left, right? Okay, this is about the convergence, but what about the optimality? How to show the convergence rate is optimal? So optimal, for that we have to show the one, we have to define one approximation class that this class will have the property that is, if P and U are your exact solution, and what is the best possible convergence rate is possible if the your mesh size mesh has n number of degree of freedom. If best possible convergence rate is minus s n raised to minus s, then our finite element method, adaptive finite element method, also achieve that convergence rate n raised to minus s. So this is nothing but but this way we will use prove the Cauchy optimality. And to prove this error that our adaptive algorithm has a best optimality result, for that we have designed one algorithm which has one algorithm. Specifically, we have made change in the marking criteria. What we have done in this particular problem, when we saw the estimator, this estimator, if you see carefully, this has 3 parts. In this estimator, first 2 parts are with the coefficient t. T is dependent on the mesh size. So as we reduce the mesh size, this estimator will reduce. But if you see the last term, the f minus fh, this it don't have the coefficient h. So it is not guaranteed that if you reduce your if you refine your mesh, then this estimator will also reduce. And our whole analysis is depend on the reduction of the estimator. So for that, what we have done, we have divided our estimator into 2 parts, which is collection of first 2, and the second is the data approximation. So plus point here is f minus fh is a given quantity. Okay, so it is totally independent of your problem. So we can distinguish these 2 parts. And what we have done, we have applied the separate molecule algorithm where we have just compared the error between data approximation and estimator. If estimator is large, then just refine according to the estimator. But if your data approximation is large, your data is not properly approximated by the given mesh, then apply the approximation algorithm. So approximation algorithm, for example, if we have given such kind of f, then obviously uniform refinement with the piecewise linear function will not give the good approximation with the uniform one. So we have used approximate algorithm to, first of all, we have to approximate your data properly. And with that mesh, we can go for the adaptive algorithm. Okay. So using this algorithm, separate marking criteria, we are able to prove this convergence and Cauchy optimality result. For that, we have first of all established the result, that is stability reduction, which is making sure that your estimator is reducing at every edge. Then discrete reliability, that at every refined mesh, we can bound the discrete error with the estimator over the discrete level. Then Cauchy orthogonality means your error is reducing at every level. And the last 2 things are about the algorithm which we are using for the data approximation. It also has a best optimal convergence rate. If we are able to prove, here we are able to prove all the properties for our separate marking criteria. So that's why we are able to prove this optimal convergence rate. So in this first article, we have proved it for the L2 norm of P and L2 norm of U error. And for in second article, we are able to prove this for the HD norm of P and L2 norm of P. So in quickly, I will go for the numerical section. So in the numerical section, I will show the 2 results. First result is here is the this is our original problem with the coefficient A is equal to I, identity matrix B is 1 2, and gamma is nothing but the, here we have taken 1, and here this is domain is L-shaped domain, and this if you see the solution has r raised to 2 by 3 sine 2 theta by 3, and if you go for the flux it will contain gradient u, and gradient u means the solution will have 1 upon r by r raised 1 by r raised to 1 by 3. The function will have singularity at the origin. So here when we apply our separate marking algorithm, this separate marking algorithm use the estimator is when we use separate marking algorithm, they compare the data approximation and the estimator. In this particular case, estimator was large, and in most of refinement, adaptive algorithm use the refinement according to the estimator, and after that we get such kind of mesh. And if we see the convergence rate, at that convergence rate, the a priori analysis was giving the suboptimal convergence rate, that is 1 by 3 using with respect to a number of degree of freedom. But in if you use the adaptive algorithm, we'll get the optimal convergence rate, that is n raised to minus 1 by 2. And another example is the when the data is not so smooth. So here in this L-shaped domain, we have taken right-hand side f, which has the discontinuity. So here basically the function f is defined as like as it is a 0 over the whole domain, but there is a 2 square like this, which is defined. This square has a function value is 1. Okay, so at that time, first when you go for the solving this problem, so here data approximation, the given data approximation is important. So when we apply adaptive separate marking algorithm over it, then algorithm was using the data approximation frequently compared to the estimator, and after that we got this adaptive mesh. And here also we got the optimal convergence rate by using separate marking algorithm. So here I would like to stop. Thank you.
Thank you,
for your
Dr. Asha Gun. You see there is a question in the chat box. Ms. Neetu Garg wants to know, please tell some basic book to learn finite element methods.
Sorry, tell me some books for
finite element methods, to learn finite element methods.
Okay, there are many standard books. One is for theory and practice of finite element method by Alexander Earn. And maybe I will put in the chat after my session is over. And then method by Professor Brenner. And yeah, there are, I will put in the chat. So,
are there any other questions?
I have a question, but if you finish technical questions, then I'll ask.
Okay. Dr. Asha, I have a question. How does your method compare with other numerical methods? Like, for example, if you had used some finite difference methods or something like that. Is there any comparison?
Right. Comparison is every method has some advantages, some disadvantages. So if I just compare with the finite difference method. Okay. So first, when we use finite difference method, so if you see, if you're solving second order differential equation, we assume function C2. Okay. And because it is totally dependent on Taylor series expansion, finite difference method. But if you see now here, when I'm solving the second order differential equation, I'm just using the u function is belongs to h10 omega. Even that is not the continuous function I'm assuming when I'm finding the discontinuous. So by that way, my right hand side is just L2, or even some many cases I can solve the problem for f belongs to h minus 1 omega. So I feel finite element method cover a lot of more general class of equation. This is the main advantages.
That is a rectangular domain. So suppose you had an irregular domain, then is it easy? How easy is it to address these questions of this well-posedness, convergence, and all this?
Right. Yeah, actually, now if it is a polygonal domain, then whole convergence analysis will be valid for any kind of domain. Even this is another advantages of finite element method. That is, if you have circular domain or some kind of circular domain or curve kind of domain, so covering that domain with the finite nodes, it is easy. But I think in a finite difference method, it will be difficult if I'm correct, if I'm not wrong. So that is. So
Sorry, go on.
for polygonal domain, yeah, whatever analysis I have shown, if it is a smooth domain or polygonal domain, analysis will work. Yeah.
Another thing I wanted to ask you is if you could explain whether you have methods for other types of PDEs like hyperbolic.
Okay. Hyperbolic. Yeah. So still now. So here I have shown the conforming, and this is mixed finite element method. So this conforming spaces will work very well for the elliptic problem and parabolic problem. But for a hyperbolic problem, there is a discontinuous Galerkin method. Discontinuous Galerkin is again a finite element method. So for hyperbolic kind of problem, so we have to use DG method. It is also popular for a hyperbolic specifically. We have to go to DG.
There is another question here from Mr. Prashant Kumar Pandey. He asks, can we use finite element methods to solve Sturm-Liouville problems?
Okay. Okay, I have to check actually. I cannot answer now. Yeah, I have to check that. Yeah.
Sturm-Liouville problems are eigenvalue problems, so yes, finite element can be used even in the higher dimensions as well. So I have replied to Prashant. I think it went as a direct message.
So Professor Riddhi, you had a question to ask.
Yeah, Asha, you can stop sharing the slide. It was a very lucid, clear lecture, and I was really pleasantly surprised. I have never met you before. So, and I know that you are from a small village in interior Maharashtra near Nasik,
Right.
and you are the first PhD in your family.
Yes. Yes.
And probably the first PhD from your village.
Yes, that's true. That's true.
Yeah. So I just would like you to tell briefly in a couple of minutes about your personal journey to, encourage our young women students. Just about yourself, little bit, just couple of minutes.
Mhm. Okay. Yeah. So yeah, as you have mentioned, yeah, I'm coming from the small village. Till now, my parents don't know what is meant by PhD. Though that don't know, they know because whatever I told to them. So before going to PhD, they don't know what is a PhD, and it was case for the most of people there. Okay, but only positive thing was I was topper in my 10th. I was topper in my BSc. So they just believe on me that whatever she is doing with passion. So yeah, so by that way, the parents were very supportive. But sometimes after MSc, many people might don't know. So option for PhD was not there in the Nasik. So after MSc, I have joined joined some job. But when I joined the job, there was something that is incomplete. So I wanted to do some more thing in the research. And then after 2-3 years, I have joined IIT Bombay for research. And yeah, and I'm very lucky to have Anila Nataraj as my supervisor. And after when I met her, most of my problem are solved, and now I have a very nice journey. So for every small things, it is not only the academic. For other than academics, she is always there for every small thing. So I always take advice from her, and I'm very happy to always talk to her. So it was difficult initially, specifically when even after 10th also, there was difficulty to, I was not sure how to, I was sure that I want to continue my education. But my parents were not sure that shall we put her into higher education or not? Because in my village, the school was up to only 10. But only I was my topper of my school. My teachers from my school, especially my headmaster and all school teachers, came to my house. They convinced my parents that no, you cannot do this. Let her go to continue her education. So I really I want to thank them too also, because only they convinced my parent to continue my education. So that's it's happened. Yeah. So my teachers played very big role in my whole education journey, because parents are not so much educated, but only thing is they have listened whatever my teachers said to me. So that is good thing. Yeah, that is there.
Thank you, Asha, for sharing your experiences. Really inspiring. And I also tell other young women students to contact you for advice on your ICER Trivandrum account. They can do that.
Yeah, sure. Yeah, sure. Yeah.
So very nice to hear and wonderful. And I think other young students, girl students, can take inspiration from you and contact you for any advice. Now you can become an advisor like your advisor. Okay.
Thank you,
Now, yeah.
Asha.
Yeah.
Yes, is there somebody who wants to say something? Dr. Asha, thank you very much for your wonderful talk and also for your very inspiring story. Yes, it does make a difference when you have supporting parents and a supporting advisor like Professor Leela Natraj. And as Professor Ridri rightly says, you can also be such a mentor for other people. Thank you very much. And we really enjoyed your talk.
Thank you.
So now I'm very pleased to introduce the session's next speaker, Professor Devanjana Mitra, Assistant Professor at IIT Bombay. She's been there since February 2018. She did her PhD at Tata Institute of Fundamental Research Center for Applied Mathematics, Bangalore, with Professor Maitri Ramaswamy on controllability and stabilizability of compressible Navier-Stokes systems in 2015. She then worked with Professor Michael Renardi at Virginia Tech for postdoc during 2016-17. She has excellent research publications in top journals like Journal of Differential Equations. Her research area is partial differential equations, in particular in linear and nonlinear PDE, controllability and stabilizability of PDEs, optimal control problems, microlocal analysis. Her talk for today is titled Stabilization of Time Periodic Flows. Welcome, Professor Devanjana.
Thank you. So shall I share?
Yes, we can see.
Okay.
So we are starting at 3:42. So you have please take 25 minutes and 5 minutes for.
Okay. So am I audible?
Yes, very much.
Okay, thank you. Yeah, so first I would like to thank the organizers for giving me the opportunity to give a talk, and thank you for the introduction also. So today I am planning to give a talk on stabilization of time periodic flows. So briefly I will discuss about the introduction and the questions what we are looking for. Then I will discuss the case for ordinary differential equation that we will call often a finite dimensional case. So there the things are mostly understood and well studied. Then the challenging part is that to adopt all these all these techniques to the case for the PD, which we will call it actually infinite dimensional setup. So for PD, I will just touch upon the result which we obtained for Navier-Stokes equation, and then I will give some reference. That is the plan for today's talk. So let us see. So first we will start with the dynamical system. Okay, sorry. Yeah, so we'll start with the dynamical system which can be posed in Rn. Then it will corresponds to the OD, ordinary differential equation. It could be system of ordinary differential equations. And when it is posed in some functional space, for example, we'll take Hilbert space setup, then it corresponds basically the partial differential equations, and then we'll call it basically the infinite dimensional system. So now let us concentrate the case for dynamical system evolving in Rn. So I will consider that y prime t equal to f y t, and f is the function. You can assume the smoothness whatever you want now. For example, the C1 smoothness is enough for our purpose. So then the question you can ask that, or we are interested in particular to understand the long time behavior of the system as time tends to infinity. So mostly the qualitative aspects of the solution of the OD. So the study of such properties often begins with the analysis of special solutions. So for example, we are interested in equilibrium points of the system and periodic solutions of the system. So equilibrium points means the yeah, I don't know why if I sorry. Yeah, so equilibrium points means the zeros of fy. So that in particular we want to find out the y such that fy is equal to 0, and then we need to understand the behavior of the solution near those such equilibrium points. Whereas the periodic solution means a closed trajectory, we'll denote it by gamma, which has periodicity with periodicity capital T for some capital T greater than 0, and gamma satisfies the dynamical system. So these are the two special cases or special solutions we will talk about. So then first we need to understand the behavior of the solution of the system when it is near the one of the special solution. So that will be determined by the stability of the dynamical system. So stability means, so I avoid the technical details here, so heuristically I am defining here the stability means that the trajectory of the solution trajectory starting close to this spatial solution remains sufficiently close to the spatial solution forever. So that we'll call about the stability property of the system. Whereas the asymptotic stability means that the solution trajectory starting near this spatial solution tends to the spatial solution as time goes to infinity. So stability theory for these spatial solutions of ODs is very much well understood, and the crucial observation is that the stability of the system can be characterized by the behavior of the spectrum of the linearized operator, and which is the suitable linearized operator and how it relates. That's what you will see in the next slide. So for now we are talking about the stability of the equilibrium points of OD. So let us consider the dynamical system as I already considered. Y prime t is equal to fyt. Then ys is an equilibrium solution provided fys is equal to 0. Now to check the stability of the equilibrium solution, the first step is you linearized the system around the equilibrium solution. Ys belongs to Rn here. So then we obtained this linearized equation given here, that is z prime t is equal to a zt, where a is particularly the differential the dfys, that's the differential map of the function f evaluated at y equal to ys, that's the equilibrium point. In particular here it is an n cross n matrix, and z is basically denoted by the difference yt minus ys, and that's how we that z prime t a z t is basically the system around the trajectory or around the equilibrium point ys, and this is the linearized version of the dynamical system around the equilibrium point ys. So here if we want to study that how or when yt belongs to ys, so in particular equivalently here we want to study that whether zt goes to 0 as t goes to infinity or not. And here it is, I think mostly it is well understood and well known that it can only happen, I mean if and only if, that the if all the eigenvalues of matrix A has negative real part. So in summary, zt goes to 0 as t goes to infinity if all eigenvalues of the operator A, that is in particular the dfys, has a real part or has a negative real part. Okay, so all are in the negative half plane in the of the complex plane. So that is the characterization when we want to study the stability around a equilibrium point of a dynamical system. So this is well known. So now how that stabilizability come? So now suppose one dynamical system is given to you, and you know or you find out that the some eigenvalues of A has positive real part. Okay, so that means the system is not stable. So then the question comes that suppose you add one parameter that to you, or one input. That's what I mean, that you here we introduce by but. B is the control operator and ut is or u is basically the control variable. So you introduce an extra parameter in the dynamical system, and now you ask the question that can you choose a control u suitably such that this controls, I mean the system with the control has the stability property. And that is particularly we talk about or we define the stabilizability of the system. So it's basically the interplay between two matrices here. One is capital A and another one is the control operator capital B. So that's what we are going to define, that what does it mean. So A, B is stabilizable if there exists another matrix capital K such that A plus BK is a stable matrix now. So suppose you find out I mean such K exists, then you write ut is equal to kzt, and then the equation, the dynamical system z prime t is nothing but equal to A plus BK the whole bracket into zt. And now you suppose know the spectrum or eigenvalues of the operator A plus BK has only negative real part, then you know that, or in particular you know that A plus BK is a stable matrix, then you know that the solution or this dynamical system Z prime T is equal to A plus BK into ZT has the stability property, or in particular the solution goes to 0 as T goes to infinity. So when we talk about or we ask to check the stabilizability of this system with control operator B, it boils down to find out or to check if such matrix capital K exists such that the spectrum of A plus BK now again lies in the left half plane in the complex plane. Okay, and how do we check this stabilizability property? Again, in finite dimensional case, what we are talking about here, that means for the OD, it is well known that is very much related one condition called Kalman rank condition or Hotu's type condition, which is precisely given here. The kernel of lambda I minus A star is the adjoint matrix and B star is also the adjoint matrix of B. So here the condition reads as follows: kernel of lambda I minus A star intersection B star is equal to phi. And I mean for all lambda whose real part of lambda is greater than equal to 0, and lambda is coming from the spectrum of the matrix capital A. So the first step is to check this condition, which is called Kalman rank condition or Hotu's type condition. And so once your answer is no, when your answer is yes, so it means that you check the condition and you showed that A, B is stabilizable. Then next task is to find out this matrix capital K in suitable way such that it gives you, or even from practical point of view also it is more meaningful. So that is the next step. But here once you have proved this Hotus type of condition or Kalman rank condition holds, then the essential idea is that it assures you that you will find out another matrix capital K that is in particular called pole assignment theorem. So the idea is that whatever the bad eigenvalues you had for capital A, we call it unstable eigenvalues, that will be pushed to the negative side of the complex plane because of the choice of capital K. And this Hotus type condition precisely gives you that that liberty to choose such matrix capital K. So this is well understood, and this is basically giving you the existence of such K. And next the goal is that how to find such control such operator K. We call it feedback operator, and that K can be obtained by studying a suitable optimization problem. So that's what I wrote it here. So this is basically the minimization problem we have to study. Is minimization of the functional J, which is basically given or defined in this particular way. Z is the trajectory of the dynamical system, and now you know that it is asymptotically stable, and U is basically the control. So U is, we call it admissible control. So that means that whatever the control sending the trajectory Z to 0 at t goes to infinity, we minimize over such control. So then we have basically this system that if A, B is stabilizable, then J has a unique minimizer, and there exists a unique symmetric positive definite operator P satisfying the Riccati equation, which reads as A star P plus PA minus PB B star P plus I is the identity, is equal to 0. So this is basically a matrix equation. And so the stabilizability, I mean, once you know that the stabilizability of AB holds, then you have two conditions which is going to be satisfied. One is that this minimizer problem has a unique solution, and the second is that this Riccati equation has also a unique solution P, such that A minus B star P is stable. And not only that, the minimizer of J, that's the minimizer's trajectory, if I if I call it by Z and U again, so then Z will satisfy this closed loop system A minus B star P ZT, whereas the control UT can be determined by minus B star P ZT. So whatever that capital K I was talking about is nothing but that minus B star P in particular. So that's how you can explicitly, and in Rn you can explicitly solve this Riccati equation, and in particular you can find out the expression of K, and that's how you can construct explicitly what could be your feedback control which stabilizes your system. So this is the story when you are doing the stability or stabilizability around an equilibrium point of a dynamical system. So this is well known now. So next, I want to see what will happen if we want to do the similar study for the periodic solution of the OD. Okay, so as we introduced earlier that gamma, say gamma is a T periodic solution of the system, and it satisfies this dynamical system again. And then the main step is to linearize the system around this trajectory periodic or say periodic orbit gamma. So if I do that, I will get again a system Z prime T is equal to AT ZT, and now the crucial thing is that this A now is a function of T. Earlier it was just a constant matrix, and everything is, so the eigenvalues are whatever spectrum we studied, everything was time independent, and nicely we got the result. But now this matrix A is a function of T. It is also, and what is the definition of AT? It's again a differential map DF at evaluated at or that periodic orbit gamma T. So it is again a n cross n matrix, but it is a T dependent it's a matrix and depends on the time T, and it is that capital T periodic, again the same periodicity what we had for the periodic orbit gamma. So that we have now. So definitely we have to change or adapt some a little bit new technique to obtain the stability criteria for such system. So what is that? First of all, how do we solve, and what is the meaning of the trajectory of the solution? Those are all, I mean, already well studied. So I'm just recalling here in particular that a fundamental matrix for the linear system that will denote it by ST, which satisfies basically the matrix differential equation, which is given here. S prime T is equal to ATST, and S0 is basically the identity operator. Okay, that we will call it fundamental matrix, and each column of this fundamental matrix is basically linearly independent. So you have n columns and n linearly independent column vectors in particular. That is the property of the fundamental matrix. So then the solution of this linearized system, whatever given here, with initial condition Z0 at t equal to 0, if I denote the solution trajectory by phi t Z0, this is nothing but equal to ST, that is the fundamental matrix I just talked about, acting over the initial vector Z0. Okay, so this is the expression of the solution trajectory corresponding to this linearized system. Here the point is that I already mentioned, now the eigenvalues of AT will time dependent. So we have to find out that how to relate the stability property of the system and which is the suitable mapping or suitable operator whose spectrum can correspond to the stability property of the system. And another issue is that since we have already studied the time independent case, that's the autonomous case, when the linearized system is the system is linearized around the equilibrium solution, and there we know how to characterize the stability. So then our next goal also could be that is there any change of variable formula or anything such that we can transform that this is basically non-autonomous system, because that A depends on T. So this non-autonomous system can be reduced to an autonomous system, and we can correspond between two systems to characterize the stability or even other qualitative property. That is our next question, and that is basically answered by Floquet theory. Any standard OD books, I suppose, already discussed about it, but I am just briefly want to mention here. So here the theorem reads as follows, that corresponding to any fundamental matrix, there exists a non-singular T periodic matrix. We will call it by QT, and Q0 is equal to again identity, and a constant n cross n matrix that is denoted by lambda, such that this ST, that was the fundamental matrix, it can be written as equal to Qt acting on e to the power lambda t. So this is the expression. So we will find out a non-singular matrix Q and a time independent, a constant matrix n cross n matrix lambda, such that the fundamental solution can be represented in this particular form. This is due to that Floquet theory we get. And once we have this, as a corollary we get that the non-autonomous system under the linear change of coordinate, that is called xt equal to q inverse t zt, reduces to the autonomous linear system x prime t is equal to lambda xt. Whatever the in the previous slide I was talking about, that let me see, yeah, that z prime t at zt, under this change of variable xt equal to q inverse t zt, now it is reduced to this autonomous linear system, which reads as x prime t is equal to lambda xt. So in particular, q is basically the diffeomorphism between these two space. And here, once we look at this autonomous linear system, here we know what the stability means. So to obtain the stability of this system, definitely the again all the eigenvalues of lambda has to be the negative real part. So that is very much well understood. So now I want to relate that what is the corresponding operator or corresponding mapping for the original AT system, that is this Z prime T AT ZT system. We should consider whose eigenvalues or whose spectrum can be determined or can be related to the spectrum of the this matrix gamma. Is there any way to do it? So that is the question, and it is again well understood from the point that I mean from very earlier stage of mathematics, I think. So this is due to the name came after the famous mathematician Henry Poincare. So I think everyone more or less we are already introduced with the that Poincare return mapping that notion. So what does it tell? So this type of concept is very much important when anyone studies this bifurcation theory or even the stability of the system and etc. So it has enormous application, and I mean it's kind of basic also to understand such cases and to define it more mathematically. So here we use the whatever the basic things we read from OD book. So it reads as follows, that if x naught belongs to the gamma, so this gamma is the periodic orbit, and this sigma is a hyperplane transversal to that periodic orbit gamma at x naught, then for x which is coming from this hyperplane sigma, it is sufficiently near to that point x naught, then the solution trajectory, whichever what I defined already by phi t x, starting from x at t equal to 0, hits the hyperplane sigma again at time t equal to capital T, where the capital T is the periodicity, if you remember, of that periodic orbit gamma. And the Poincare so it gives you that it at the time t equal to capital T, the trajectory will hit this hyperplane sigma again, and whatever the point he at whatever the point that trajectory is hitting that sigma, let us call it by p. So now the Poincare return map u basically associates to the point p, which is nothing but this phi at evaluated at capital T, and which I mean x was the initial condition. So in particular, what I was trying to tell, that Poincare return map u is defined in this particular way, where ux is equal to phi at evaluated at capital T, and x was the initial condition. So that's how we define this Poincare return map, and it is easily one can observe that u x naught is equal to x naught if and only if x naught is coming from the periodic orbit, because this phi will be then that gamma if x naught is coming from the gamma, and that will give you the fixed point of this Poincare map u. So in other way, the stability of the periodic orbit is then equivalent to the stability to the fixed point of the map u. So yeah, so this is the correspondence between
Excuse me,
the
Dr. Devanjana, can
yeah.
you please hurry up?
Yes, please. Yeah, sorry. Yeah. Okay, yeah, so this was explained here, and so the idea is that the stability of the dynamical system can be yeah, it is correspond to the stability of the fixed point of the map U. So that is what is studied in I mean, it's already started. So the stability of the fixed point x naught of the map is determined by the fact that again, if we take the differential map of u at the point x naught, the norm of du x naught has to be strictly less than 1. And then Floquet theory gives in particular that norm of du x naught is equal to e to the power sigma t. And we have already seen that x prime t, that lambda xt, it can be stable if and only if all the eigenvalues of lambda has to be negative. So that is corresponds in the fact, that is in summary, this is the last line, that stability of the system can be obtained if and only that modulus of lambda j is strictly less than 1. So now it is less than unit modulus for all eigenvalues. I mean, lambda j's are the eigenvalues of the operator du x naught. Okay, so this is the stability property we obtained when it is linearized around a periodic trajectory, and this is very much related to the spectrum of the Poincare map. So that's what I wanted to point out. Yeah, so then again you can ask the stabilizability question, and you can again find out the control operator or feedback operator by solving a suitable Riccati equation. So all these things is well understood for the system, for the ordinary differential equation. I will just briefly mention the compressible Navier-Stokes equation, and then I will end. Maybe I'll get 2-3 minutes more.
Yes, please.
Okay. Yeah. Yeah, so our goal was to adopt all this idea in particular to the case for Navier-Stokes equation. So first of all, the Navier-Stokes equation is very much is interesting to all of us. So one reason is that from practical point of view, this Navier-Stokes equation model basically the fluid flow, and it arises in several other field also. For example, that aerospace sciences, math, biology, and physics, and so on and so forth. Not only that, even from mathematical point of view, the existence or the qualitative behavior of understanding of qualitative behavior of the solution of this system is also fully not known, and especially it is in R3, that is a Clay Millennium Prize problem. It is still open. So I gave that link here, so if anyone interested, they can see the what is the problem posed there. So in summary, it is very much interested to we are very much interested to study the long time behavior, and especially around the equilibrium point and then periodic orbit. So near equilibrium point, it is more or less well understood. What we wanted to do, the stability or stabilizability around a periodic trajectory, and for that the goal was that can we write it into a operator form. So it is a dynamical system, but now instead of posing it, now it is posed in a suitable functional space, and we consider a Hilbert space setup instead of Rn. So now the challenge is that whatever we consider there, the fundamental solution, the solution trajectory, and the Poincare map, and etc., we have to give a equivalent or analogous definition or statement for this case when the dynamical system is posed in the Hilbert space instead of Rn. So that was the challenging part, and there are few references already. So I will just mention that, okay, once you have, I wrote it also very heuristically because I wanted to avoid the technical details. So here in particular, suppose you know that your operators AT and the control operators BT satisfy some required or suitable condition, then particularly you can show that there exists a evolution operator S T tau I defined here, which is basically corresponding to that fundamental solution what I was talking about earlier in the OD setup. So once you have this, then you can define an analogous Poincare map here again. So this is defined by in this particular form. And here we need to study the behavior of this Poincare map explicitly, and in particular we obtain such a result that the map is basically T periodic. Most importantly, the spectrum of this Poincare map we wanted to know, and that turns out that it has a the other than zero, whatever the elements it has in the spectrum, it will all will be eigenvalues and they will be independent of T, and it has this decreasing property, and modulus of lambda j is going to 0 as j goes to infinity. Those are the crucial properties we used earlier also implicitly, and now it will be used explicitly, but I skipped all the details. So now once you have all this setup, the conclusion is that yes, now you are in the suitable in the position to check the stabilizability of the system. And to do that, in particular we had to prove a unique continuation property which corresponds to a ocean system. And once the answer was yes, then the next step was to construct the feedback operator via some periodic Riccati equation, and the answer was yes, that we are able to do it. And then once we stabilized the linearized system, then the control used even to stabilize the nonlinear system using a fixed point theory. So I just briefly mentioned all this, I know. So for the details I refer our these two papers, which is in the MathSciNet, I think. And I briefly mentioned, okay, so yeah, I want to thank my collaborators also. So it was a joint work from with Mehdi Badra and Professor Jean-Pierre Remo from Toulouse, and Professor Maithili Ramaswamy. She is in ICTS now. And so that was the outcome of our collaboration. And then we want to refer few references which we used, and I want to finish it here. So thank you. Yeah.
Thank you, Professor Devanjana Mitra. I'm almost feel sorry to remind you
No,
of
it's
the
fine.
time.
No, I also didn't notice. Yeah, so
Yeah.
fine. Yeah.
So, are there any questions? I just have one question, Professor Devanjana. I wanted to ask you that your thesis was on compressible Navier-Stokes equations, right? But
Yes.
here the equation you showed that was incompressible.
Yes. So this is afterwards we did. So that is not my thesis work. Yeah, I worked on both actually, compressible, and this is in particular incompressible Navier-Stokes. Yeah.
So what's the difference?
Compressible equation, here we had this incompressibility property, that is divergence z equal to 0. So that is the incompressible property. And the compressible Navier-Stokes, we don't have this property, but instead of we have a momentum equation, or which involves the density. So that compressible Navier-Stokes is basically a coupling between a parabolic equation, which is mostly like heat equation, that is correspond to velocity, and the other equation is basically like transport. So that is correspond to the density variable. So here we don't have density, no, because of this incompressible property. And here we have only Z and P. So they are the compressible Navier-Stokes was actually in two variable. That was rho and Z in particular, and rho was the density equation, and pressure P was an isothermal system we considered. So P was a function of rho, so that was already taken care of. And then the second equation Z was mostly like heat equation. Yeah, it's a parabolic equation.
Okay, thank you. There's that couple of questions. One is the this is I think from Professor Nikita Agarwal. Is the area stabilizability condition necessary and sufficient, and one from Professor Srimai Bora did not get the stabilizability condition.
Can I see that?
I think this is on slide 6.
So slide 6, Debanjana, you
Yes,
mentioned
yes.
stabilizability condition, right?
Yes, yes. Yeah, let me go back. This one? Yeah.
Yeah,
Yes,
that last
this
one.
last one. Yes.
Yeah.
It's,
Oh, yeah. So kernel, yeah, the second term I forgot, that will be kernel of B star. That's what the confusion.
Ah, okay.
Yeah, kernel of lambda. Yeah, so it what is meant that kernel of lambda I minus A star intersection kernel of B star is equal to 0. Yeah, phi. So there is no common kernel. Yeah.
So is it necessary and sufficient condition?
Yes.
Okay,
Yes. If and only. Yeah. Yeah. So there was a typo. Yeah. Thank you.
And just one, can I ask a quick question, comment?
Yes,
Okay.
yes.
So Debanjana, you mentioned that Floquet theory gives us a linearization, right? So x prime t is lambda xt. Right?
Yeah, I mean the mostly I meant that Floquet theory gives that representation of ST. I think that Q and
yes. So we
just,
have
this one. Yeah, that first part mainly.
yes. So this corollary, right?
Yes.
So you have this like a linear system, right?
Yes.
So it doesn't depend on the point that you choose on the orbit, right? So
no, yeah. So it depends on the gamma basically. Yeah, I mean the periodic orbit. Yeah.
So it's quite interesting that it doesn't depend. So for the entire orbit, you're getting the same system, right? Because when you look at the entire orbit, then you would
no, but no. That one thing is that JT was yeah, that's true. Yeah, but yeah. I think yeah.
So it's independent
of the choice of x naught. That's what you mean. Yeah.
And same is true with Poincaré's map, right?
Yeah, that's also all.
So in practice, would one choose one of these two techniques? I mean, they are fundamentally different, right? Floquet theory is inspired from the earlier thing that you described, right?
Yes.
And this is something else, Poincaré return map and so on. So in practice,
so in practice they tell that to find out this ST is also a non-trivial, the fundamental solution. Solving a fundamental solution is not a trivial problem. So it depends which information is easily available. Suppose you know the trajectory and find out your Poincare map easily, then maybe the second one is more doable. And in some cases, suppose the fundamental matrix that ST is easily available, then maybe this approach, this gamma, I mean this change of variable formula and this approach may be useful.
Okay. That's right. Thanks, Debanjana.
Thank you, Professor Debanjana. It was a very interesting talk. Really enjoyed hearing you. Professor Vithi?
Yeah, Debanjana, can you briefly in a minute tell us about yourself for the young audience? And you can stop sharing the screen.
Yeah, just trying to find out where it is.
Doesn't matter, you just tell us briefly because
meanwhile, Carolina is there, so she can be made a co-host.
Yeah, I will tell Sagni.
Actually my parents both are teacher and in education.
Carolina came here.
Go ahead, Debanjana.
So mostly I mean they were supportive, so everything went well from then. And then when I joined in TIFR also, I got enormous help from Professor Maithili as a PhD guide, and we had a good collaborative group also in CAM and later on. So that somehow helped to grow even as a in research world, and to be an independent researcher and etc. Yeah, and then here in Bombay also we have Neela is there, and so we have a good community, and so more or less it went smoothly. So that's what I can tell. Yeah.
That's nice to hear. Very interesting talk you gave. I was really happy to see this and Poincaré written map and all. It is quite close to my heart. So you are older than Asha and you have more experience. So can I ask our young women students to contact you for
sure.
advice?
Sure. Yeah.
So participants, you may do so. She is in IIT Bombay and she would have her email ID on her website. So you can contact her for any advice, information, chat, whatever you like. Thank you, Debanjana, and thank you, Padmavati, for chairing both the sessions. Our next talk, okay. Our next talk is by Professor Carolina Araujo, and that would be soon in about 5 minutes. So we have 5 minutes break. Maybe we have 4 minutes break.
Hello.
Hi.
Hello. Hi.
Hello, Didi. Hello, Gita.
Hi.
Hi, Neela.
So I looked up the time. It's 8 in the morning, around 8 in the morning. So we're just starting the day.
Yes, unfortunately, I could only get the final part of the previous talk. It would be very hard for me to actually attend the whole conference, which is a pity. But,
yeah, there was recently a 24-hour conference because of the time differences. They just ran the conference for about 24 hours and they listed all the speakers. So whichever time zone suited you, you could go and attend that conference.
that is nice. Well, of course, you cannot attend all, so.
Yes, it was a 24-hour one.
So Carolina, you would be able to share the screen, no? Do you want to try once?
Yes, I can try. Let me see.
We are glad that you can make it even at the end of the day. So.
Yes.
Yeah, that's fine. Wonderful.
That's fine. And you're able to change the slide? Just check that also.
Okay. Yes.
Yes.
Okay.
So in fact, I prepared 2 presentations, one for the math, and then if you afterwards is interested in learning some of my activities regarding women in mathematics, I have then a separate presentation. So I try to make my math presentation a bit shorter so that I have time to talk about other things as well.
I think that's one of the primary purposes of the conference, that young women and others get to know of all the different activities that are there, particularly involving women.
Okay.
So how old is your son now?
He's 5 years old.
5 years. And he allows you to, he must be having online education now. How is it as a 5-year-old?
So he spent 1 year outside school last year because of the pandemic. The schools closed and he was too young to understand this video conference. So now this year, in the beginning of March, the schools finally resumed, but now we are locked down. So we'll see. It's very hard for the children. but he's sleepy. So it may happen that during my talk he wakes up, and then, but I try to be a bit far from the room, but we'll see.
You're having all your teaching online as well for the
Yes.
IMPA?
Yes, everything is remote for the moment.
We've been opening up slowly. Our PhD scholars and maybe final year students are coming into the university, but cases are going up in India also, and various states have gone into lockdown. Not the country as a whole, but some areas. So it's still a difficult time.
Yes, yes.
Riddhi, you'll have to tell me when to start.
In half a minute, I will say something, then you can. Okay. Wait. Just wait. Yeah. So I think we have how many people now? 80 people, right? Or what? Yeah. So it's 4:30, and can we start? Neela, are you there? Okay.
Yeah, we should.
Okay. So welcome to our evening talk by Professor Carolina Araújo from IMPA, Brazil, and we are very glad that she had agreed to talk here given the big time difference. And this talk is going to be chaired by Professor Geeta Venkatraman from Ambedkar University, Delhi. Over to you, Geeta.
Thank you, Riddhi, and good morning to you, Carolina. It's 8 in the morning in Rio, and Carolina's just joined us at the conference. And it's my pleasure to welcome you, and I'm going to take a couple of minutes to say a few things about you. I'm sure most of our audience already knows you, but it gives me great pleasure to introduce you to the audience. So Carolina Araújo is a full researcher at the Institute of Pure and Applied Mathematics at Rio, Brazil. And full researcher is the highest level, I believe, that you can have at IMPA. And so Carolina is at IMPA. She has loved mathematics since high school, but during her undergraduate studies, she initially thought of pursuing engineering or physics until, as she says, she took her first serious mathematics course in analysis. After that, it was engineering's loss and mathematics' gain, as she went on to pursue a PhD in Princeton University in mathematics. And she then returned to Brazil for a postdoc at IMPA and successfully made not only tenure but has reached the highest level possible at IMPA. Carolina has many achievements to her credit. She is currently the Vice President of the International Mathematical Union's Committee for Women in Mathematics. And she was a key organizer of WM Square, as it was known, the World Meeting for Women in Mathematics in 2018. This was an event which preceded the International Congress of Mathematicians, which was held in Rio in 2018. She was recently awarded the Ramanujan Prize in 2020 for a young mathematician for her outstanding work in algebraic geometry. And from 2015 to 2020, she was a Simons Associate at ICTP, the International Center for Theoretical Physics. Carolina's area of research is complex algebraic geometry with a focus on birational geometry. Today, we are very happy to have Carolina with us to give a talk titled Symmetries in Algebraic Geometry. So Carolina, could I request you to start your lecture?
Sure. Thank you very much, Geeta, for this very generous presentation. And I would like to thank the organizers for inviting me to give this lecture. Let me just share my screen. Okay, so I would like to start with a mathematical presentation about my research. And afterwards, I have also prepared some other slides to talk about some of my activities regarding women in mathematics. So today I would like to discuss symmetries in algebraic geometry. So when you study, so when you study some mathematical object, you are often interested in understanding its symmetries. So this may be symmetries of a geometric object or of some system of equations or basically any area of mathematics. For this talk, we are going to be interested in symmetries of complex projective varieties. So these are complex varieties that are defined by polynomial equations. So here I put some pictures of complex projective varieties that have some symmetries. And then you can see that in the first case on the left, you can see that there is a finite group of symmetries, while in the second one, we have an infinite group of symmetries. So let's analyze these cases more carefully. So let me first introduce more precisely the objects that we are considering. So this is the first notion of symmetry that I would like to discuss. So we are working, as I said, with projective varieties. So these are complex varieties defined as solutions of polynomial equations. Then we have a notions of morphism between two such varieties. So this is just a map F that is given coordinate-wise by polynomial equations, or at least locally they are modeled like this. So locally, at every point, you can define the map by polynomial equations, polynomial coordinates. Okay, so then we can define the group of automorphisms. So this is just a group of invertible morphisms of X into itself. So this is the first notion of symmetry that we would like to consider. And let's take as an example the projective space Pn. So in the case n equals 1, this is just the Riemann sphere. So this is what I have illustrated in this slide. And the automorphism group is just a group of invertible linear maps. So this is PGLn+1. So this is very well known. So this is in particular, it's a very, very interesting linear group. Okay, more generally, we have, if you have X, any complex projective variety, you can consider its automorphism group, and it has a structure of a Lie group. So I don't know what happened with my slide. Now there is a red line. I don't know how I did this, but I'm sorry for that. So, so the automorphism group of X has a structure of a Lie group. And so we can look at the connected component of the identity. This is a complex algebraic group. And in general, what we have is a exact sequence like that. Maybe I should have ones in the ends to illustrate that this is an exact sequence of groups. So you have this connected component of the identity, which is a complex connected algebraic group. And in the co-kernel is a countable discrete group. So let's look at this and let's understand this in a few examples. So the first example that I would like to discuss is the example of a smooth projective curve of genus G. So in dimension 1, we have this trichotomy, this very important trichotomy of positive curvature, zero curvature, and negative curvature. In terms of the genus, this is genus 0, genus 1, and genus greater or equal than 2. And let me say that this trichotomy for smooth projective curves, which is the same as Riemann sphere, this trichotomy is present from many different aspects. So from the point of view of curvature, from the point of view of fundamental group, from the point of view of rational points when you look at the solutions over the rational numbers and so on. And we also see this trichotomy from the point of view of symmetries, of automorphism. So in the first case, genus 0, this is just the Riemann sphere. So this is just the projective line P1. In this case, the automorphism group, as we saw before, is PGL2C. So this is a fine variety. So this has a structure itself of algebraic variety. The case genus equals 1. So this is the case of the torus. And so this is what we call an elliptic curve. And it has a structure, the variety itself, the curve itself has a structure of a group. So X itself is a group, and it is the connected component of the identity. And then the discrete part in this case is finite. And in the case of genus at least 2, the automorphism group is finite. So we have very different behaviors. So even though genus 0 and genus 1, we both have an infinite group, which has a structure of an algebraic variety, they have very different natures. The first case for genus 0, this is a fine variety, while in the second case, genus 1, this is a projective variety. So there is a difference in these two cases. And in general, we see a mix of these three behaviors. So now let me look at another important case, which is that of automorphisms of smooth hypersurfaces. So by a hypersurface, I mean a algebraic variety, a projective variety that is defined by a unique equation. So in this case, we say that the hypersurface has degree D if its defining equation has degree D. Now we would like to understand the automorphisms of this hypersurface. And then here there is this beautiful theorem by Matsumura and Monsky back from 1964 that says that the automorphisms of a hypersurface are always induced by linear automorphism of the ambient space, except in two cases. The case ND equals 1, 3, so that is a cubic plane curve, and ND equals 2, 4, which is a quartic surface in P3. So let us look at these examples more carefully. So in the case of a elliptic curve, so this is the curve of genus 1. So as we saw before, it has an infinite automorphism group, and it contains, this automorphism group contains the curve itself as the connected component of the identity. And in the case of a K3 surface, so the case of a quartic surface, this is known as a K3 surface, a smooth quartic surface in P3. It's an example of a K3 surface. And in this case, the automorphism group varies depending on the equation of the quartic. It is always discrete, but in some cases it may be finite, in some cases it may be infinite. So this is actually a very rich area of study, understanding the automorphism of quartic hypersurfaces in P3. On the other hand, in both cases, the image of the subgroup of automorphism that is induced by a linear automorphism of the ambient space is a finite subgroup. So then we may ask, so where do the other automorphisms come from? If they do not come from an automorphism of the ambient space, is there another way to describe them? So this is a question that I will come back to at the end of my talk. But now I would like to argue that in birational geometry, the notion of automorphism is way too rigid for many purposes. So I will try to explain this in these slides. So let me first explain to you what is birational geometry. So this is a sub-area within algebraic geometry where we aim at classifying projective varieties. So let me discuss the classification problem in algebraic geometry. So first, in dimension 1. So in dimension 1, this was pretty much done by Riemann back in the 19th century. We have first, we classify our curves or Riemann surfaces according to a discrete invariant, in this case, the genus. So we fix the genus and then we put together all the Riemann surfaces or complex curves of genus G. And then once you fix the genus, you have a moduli space. So now you have a continuous family, which we call a moduli space of curves of genus G. So this is again, an algebraic variety that is parametrizing isomorphism classes of curves of genus G. And if the genus is greater than 0, then actually we have an infinite family of such curves. So from the point of Riemann surfaces, this moduli space would be parametrizing different complex structures that you can put on a compact surface of genus G. Okay, in higher dimensions, the classification problem has to be modified. And this is because there are too many isomorphism classes to try to organize them in this way. So let me give you a precise example. And for that, I will explain to you a very important construction in algebraic geometry, which is that of a blow-up. So let me define first the blow-up of P2, the projective, complex projective plane in a point. So we take, I put a drawing of the P2 with a point, and to blow up a point means that we are going to make a modification in the plane, in our original plane, and we are going to substitute that point by a P1 of all, consisting of all the tangent directions of the plane at that point. So we see that we have all these lines that pass through the point in the plane. When we blow up, these lines get all separated. So so this is the intuitive definition, but in the case of P2, I can give you a precise construction of the blow up. So let me, to be precise, let me fix the point with projective coordinates 0, 0, 1 in P2. So this is my point P. And what I do is the following. I consider the projection. So this is what I wrote in blue. I consider the projection from the projective plane to P1. So I project from the point. So I take a P1, a line that does not pass through the point. And for every point in the plane that is different than P, I connect my point to P, and I take it to the point of intersection, the unique point of intersection with the line. So this is the projection, what we call the projection from a point. And in terms of coordinates, is given as I wrote in blue. So this map is not defined at the point from which I am projecting. So this is the only point where the map is not defined. And so what I can do to construct concretely the blow up is to take the graph of this map from P2 minus the point to P1. So this leaves inside P2 cross P1. And I take the closure of this graph. So this is what I call X tilde, which is the blow up of P2 in one point. Then we see that the outside the point, I have an isomorphism, but the inverse image of the point is exactly a P1 consisting of all the tangent directions at that point. And outside this P1 and if I remove this P1 from the blow up and I remove P from the plane, I get an isomorphism. So this is what we call, this is a very important construction in algebraic geometry. So this is why I decided to explain it in details. And you can actually generalize this construction to blow up any variety at a point P. And even more, you can blow up any variety along any proper subvariety. So now let me just point out that in general, what we will have is we are going to replace the subvariety Z. Each point of the subvariety is going to be substituted by the projective space of normal directions of Z in X at this point. So we have, again, an isomorphism between dense open subsets of the blow up and the original variety. Let me observe that if we try to do this for a curve, we don't get anything new, because if we blow up a point in a curve, we substitute this point by its tangent directions, but there is only one tangent direction. So blowing up a smooth curve does not change it. But as soon as you blow up points on a surface, you create a new surface, not isomorphic to the original one. And then I can continue blowing up points in as many points as I want. And in this way, I can construct uncountably many non-isomorphic surfaces. And because they are very similar, each two of them, they are isomorphic on some dense open subset, but they are not isomorphic. So there are way too many isomorphism classes of algebraic surfaces. And so what we do is, instead of classifying up to isomorphism, we are going to classify projective variety up to a more coerce equivalence, which is the birational equivalence. So this is what I define now. I say that two varieties are birationally equivalent if they contain dense open subsets which are isomorphic. So this is example, for example, as in the case of the blow up. If I blow up a point in the plane, I get a new surface which is not isomorphic to it, but it's birationally equivalent. And now the problem of birational classification becomes the following. Given a projective variety X, we would like to find a simplest representative in its birational class. So this is what we call the minimal model of X, or a minimal model. Usually there are different simplest representatives. And then after we can do this, then we would like to fix some discrete invariants and then construct a moduli space of minimal models having those discrete invariants. So this is roughly speaking how we address the problem of birational classification in algebraic geometry. Okay, so in this talk, I will be more concerned with the first, so let me discuss the first part of this project, which is to, given a projective variety, to find a simplest representative. So this is achieved by the so-called minimal model program. So this is a very important area of algebraic geometry. The minimal model program, so I don't want to say exactly how it works, but what it does for you, it's if you give me a complex projective variety, I run a certain program, a theoretical program, and then in the end, the output is going to be a simplest representative in its birational class. So let me just tell you a bit about the development of the minimal model program. So in dimension 1, so these are Riemann surfaces. This program is basically Riemann's work in the 19th century. In dimension 2, this was achieved by the Italian school in the early 20th century. And then from dimension 2 to dimension 3, there were serious obstacles that needed many different new theories to be developed. And finally, actually, with the work of many mathematicians, it was finally completed by Mori in 1988. So this work yielded him the Fields Medal in 1990. And then in arbitrary dimension, this is the full program is still not available, but we have quite a lot of advances that is enough for many purposes due to Birkar, Caccini, Haken, McKernan, more recently, 2010. Okay, so this is just to tell you a little bit about the minimal model program, which is a central area within algebraic geometry. And now let me discuss another problem. So now, once we have the minimal model program, we may be interested in understanding when two varieties belong to the same birational class. For instance, let's take one of the simplest projective varieties, the projective space itself, Pn. Then we say that a variety is rational, a complex projective variety is rational if it is birationally equivalent to Pn. And so this is now a very important problem in birational geometry. Which algebraic varieties are rational? So even more concretely, and this is surprisingly still open in many aspects, given the degree d and the dimension n, is the generic hypersurface of degree d in Pn plus 1 rational? So some instances of this problem are easy and have been solved, but some very simple problems have not been answered yet. So I would like to focus on that, and let me just give you some examples. So to start, we have a necessary condition that in order such a hypersurface can only be rational if the degree is small enough, if it is less or equal than n plus 1. So, and this is easy to get. This is just to compute the dimension. This is to compute some birational invariants that give you this bound. So I do not want to get too much into this. But now, let me give you then an example. So as I said, we have this necessary condition. So in order to be rational, the degree has to be small. So let's look at some small degree hypersurface. So for instance, a quadratic hypersurface. A quadratic hypersurface is given by a polynomial of degree 2. So this is, this is what we usually call a quadratic. In this case, because the polynomial has degree 2, if you take any line in the projective space, it will intersect the hypersurface precisely in 2 points, possibly counted with multiplicity. And this allows us to easily construct a birational equivalence between the quadratic and Pn. And this is what we call usually the stereographic projection. So we take a point in our quadratic hypersurface, and then we project from there. And this is the same projection as I explained to you in the plane. And because each line intersects the quadratic hypersurface in 2 points, then this gives us a birational map. We can construct a inverse or a birational inverse. Okay, so for quadratic hypersurfaces, then we see that they are rational. And now already, let me just point out that already for degree 3, this is an open problem. So for n equals 3, this is known. It is not rational. In dimension 2, a cubic surface is rational. In dimension 3, a cubic threefold is not rational. And or the generic cubic surface is not rational, but it's not known already in dimension 4 whether the generic cubic hypersurface is rational or not. So this is a very important problem in birational geometry. Okay, so if we are interested in this type of problems, then we need to find invariants. So if you want to distinguish or if you want to distinguish two varieties up to in terms of birational equivalence, then we need to find birational invariants. And so this is a problem. Let's find invariants. So which properties are invariants under birational equivalence? And now we come back to automorphism, and now I will be able to justify why automorphisms are not good for these purposes. So the automorphism group of a variety is not a birational invariant. And so let's see, suppose that you have 2 varieties that are birationally equivalent, X and Y, and we may have an automorphism of X, but then when we compose, we do not necessarily get an automorphism of Y. We only get a birational self-map of Y. And so automorphisms groups are not a birational equivalent. On the other hand, we can consider the birational group of a variety. So this is the group of my birational self-map of a variety, and this is a birational invariant. So this is the new type of symmetry that I would like to consider from now on, the group of birational self-maps of a projective variety. So this is the birational group, and I am especially interested in the case of, okay, so before I go on, so just as an example to show that this is actually really useful, Iskowski and Manning use the birational group to distinguish the quartic threefold from P3. So they computed the birational group of the quartic, and they checked that it is different than the birational group of P3. And in this way, they showed that a smooth quartic threefold is irrational. Okay, so now from now on in my talk, I would like to discuss the Cremona group. So the Cremona group is the group of birational self-maps of Pn. And this is a very classical object. So in the plane, so let me just say that it includes as a subgroup the automorphism group, but I will show you an example where it shows that it's much more than automorphism. So the simplest element of the Cremona group of the plane that is not an automorphism is this so-called standard quadratic transformation. So in projective coordinates, I described in these two ways. First, as I take points with projective coordinates x, y, and z, and I take it to 1 over x, 1 over y, and 1 over z. So if I look at this from this point of view, I see that it is an involution. But in projective space, we can multiply all the coordinates by the same scalar. So if I multiply everything by x, y, z, then I get to the second description, and yz, xz, and xy. So this is why it's called a quadratic transformation, because it's given by polynomials of degree 2. So I put a drawing of the standard quadratic transformation. So this map, this birational map, is not defined precisely at the 3 coordinate points. So if you try to plug in, you see that you get 0, 0, 0 which is not a point of P2. And moreover, if you look at what it does with the 3 coordinate lines, you will see that they are going to be contracted to the opposite coordinate point. So this is the geometry of the standard quadratic transformation. And then we have this beautiful theorem by Neder-Castelnuovo, classical theorem, that says that the Cremona group of the plane is generated by the automorphism and then this one simple quadratic transformation. So this is an important classical theorem. And then you may think that having this theorem, you know everything that you want about this group. And this is far from being true, even though you have a very simple description in terms of generators. This group is very complicated. And only very recently, we learned some very basic important properties of this group. So let me give you 2 examples. So only in 2013, we learned that the Cremona group of the plane is not a simple group. So this is a theorem of Cantat and Lamy. And also very recently, we obtained the complete classification of finite subgroups of the Cremona group. So this study of finite subgroups started with works of Bertini in the 19th century and was only completed recently by Dolgachev and Skovsky in 2009. Now let me discuss the Cremona group in higher dimensions. So there is a big difference between dimension 2 and higher dimension. So I recall the Neder-Castelnuovo theorem that gives us a strong factorization for Cremona groups and for the Cremona group in the plane. And in contrast, in higher dimensions, Ilda Hudson already knew in 1927 that in higher dimensions, for n greater or equal than 3, the Cremona group cannot be generated by elements of bounded degree. What I mean by degree here is the degree of the defining polynomials. So for instance, automorphisms are given by linear polynomials, so they have degree 1. The standard quadratic transformation has degree 2. It's given by quadratic polynomials. And if you have a set of generators for the Cremona group, which we don't have at this moment, but if you have some set, it has to contain elements of arbitrarily large degree. And so we do not have such a strong factorization theorem as the one of Neder-Castelnuovo. However, recently there has been many activities to understand this group. And let me just mention this beautiful theorem by Blanc, Lamy, and Zimmerman. That they produce many quotients of the Cremona group, which are isomorphic to the cyclic group of order 2. So in particular, they show that also in higher dimensions, this group is not a simple group. So how can we study this group if we do not have a nice set of generators? So if we don't have a strong factorization theorem, and so let me describe this. So I don't know what's, so I don't know what's going on with my slides, sorry. So we have this weak factorization theorem for Cremona transformations, which is called the Sarkisov program. So the Sarkisov program says that, okay, if you are given a Cremona transformation of Pn, which I call psi, then I can decompose it in very simple steps. So this psi I are called elementary links. And so these are actually very easy to describe. They're simple birational transformations. But the subtlety here is that the intermediate varieties may not be Pn itself. So in order to get a decomposition theorem in terms of elementary birational maps, you have to allow for other varieties in the middle. So these are what we called Mori fiber spaces. So these are possible outcomes of the more minimal model program. So remember, I told you that when you have to, in the minimal model program, given a projective variety, it gives a simplest representative in its birational class, but this simplest representative is not unique. So basically what we have to allow in the intermediate varieties are all this possible simplest representative in the class of rational varieties. Okay, so this is a very powerful tool to study the Cremona group, and this is the tool that some of the tools that I have also been studying. And now let me go back and put this theory of birational transformations together, linked with the theory of automorphism of smooth hypersurface. So I recall that what we saw before, that if you have a smooth hypersurface of degree D, except in the case of an elliptic curve, cubic in P2, and a K3 surface, quartic in P3, the automorphism group is induced by linear automorphism of the ambient space. And now, this is what we can, so now let's see what happens in the case of an elliptic curve. Then there is this, this very nice theorem. So this is a folklore theorem. I don't really know who to attribute it to. It says that every automorphism of the elliptic curve is induced not necessarily by an automorphism of P2, but by a Cremona transformation of P2. And so this is very well known. And now we can ask the same thing for the K3 surface case. So let me pose this question. So this question was originally asked by Giza Tulen and first addressed by Ogiso in a paper of 2013. So the question is every automorphism of S induced by a Cremona transformation of the ambient space P3? So this was asked by Giza Tulen. So Ogiso answered it negatively. So he exhibited a a quartic K3 surface in P3, having group of automorphisms infinite cyclic, and for which the generator is not induced by a Cremona transformation of P3. So this is a very interesting example, and it opens the door to trying to understand this question more deeply. And so this is a problem that I have been investigating together with my collaborators Alessio Corti and Alex Massarenti. We've been trying to understand the group of birational transformations of P3 that stabilize the quartic surface S. And then once we have this, we have a restriction homomorphism from this group of birational the Cremona transformations that stabilize S to the automorphism of S. So we've been trying to understand these maps. And for that, we consider the tool that we use is this notion of volume preserving Cremona transformation. So let me give you an example. So inside of P2, let's consider this meromorphic volume form, the x over x wedge dy over x. So this is a meromorphic volume form having simple poles along the triangle. The triangle for me is the 3-coordinate axis of P2. And one may ask, what is the subgroup of the Cremona group consisting of Cremona transformations that preserve this meromorphic volume form? So this was studied by Blanc, and he gave some nice generators for this group. So there is the first part in pink and blue, which is the part that preserves the torus. You have the torus itself acting by translation, and SL2Z acting by monomial transformations. And then you have so this is the part that preserves the torus. And then you have to add another element. So this is an element of order 5, and which also preserves the form, and they generate the whole group. And here, of course, you may, a natural problem that arises is to describe the group of, to generalize this to higher dimensions and describe the group of birational transformations of Pn that preserve the natural volume form of the torus. So this is an open problem, and now I would like to connect this with the previous problems that I discussed, the one of automorphisms of K3 surfaces. So in general, if I fix any meromorphic volume form on Pn, I can look at the group of birational of Cremona transformations that preserve this volume form. Now, associated to a volume form, I have an element of the second cohomology group. So this is, I'm just looking at the hypersurfaces of zeros, where this meromorphic volume form vanishes, and the hypersurfaces of poles, counted with multiplicity. So this gives me an element in the second cohomology group. And the observation is that, conversely, if you give me any hypersurface of degree n+1 in Pn, for instance, a K3 quartic surface in P3, then there exists a unique up to scaling volume form that does not vanish and has poles, simple poles, precisely along this hypersurface. So this is what I mean by writing down this equality. And then here, and then the problem that we have been considering is to describe this group of Cremona transformations that preserve this volume form. Now, so now we want to understand this group, and let me just, the remark here is that when the hypersurface X is mildly singular, you can think of it as being smooth, then the group of birational transformations, Cremona transformations that preserve the form is the same thing, the condition of preserving the form is the same thing as stabilizing the hypersurface. And so these are the two different problems that I discussed, understanding the group of Cremona transformations that, say, stabilize a quartic hypersurface, and then describing the group of birational transformations that preserve a volume form. And when the hypersurface is mildly singular. For those that know a little bit more of birational geometry and the minimal model program, the precise notion is that the pair has canonical singularities. Then preserving the form is the same thing as preserving the hypersurface. And then the tools that we use this is again the Sarkisov program, but a special version of the Sarkisov program for volume preserving maps. So there is a more recent version of the Sarkisov program that says that a volume preserving birational map of Pn is a composition of volume preserving Sarkisov links. So I do not want to get too much into it, but this is just a refined notion, a refined version of the Sarkisov program. And exploiting this tool, this is the first theorem that we prove. So we prove that if you take a very general hypersurface, then actually the group of Cremona transformations that preserve the hypersurface is the same thing as the group of automorphism of the hypersurface. So this of the projective space preserving the hypersurface. So there is not much, so this group is not very interesting. So if you want to produce interesting subgroups of the Cremona group, then you should look at more at special hypersurfaces. A very general hypersurface is not going to do the job. So then we started to study some special hypersurfaces, and I just want to give you this example because it's very nice, because it's very concrete. So we take a general quartic surface with one singular point. So in coordinates, I can fix coordinates, so it's given explicitly by an equation like this. So this surface has a singular point at P, and locally at P, the singularity looks like the singularity of this quadric cone in green. So this quadric cone in green is precisely the cone given by the quadric polynomial A2 in green. And here, we want to understand the restriction homomorphism. In this case, it's very easy to see that the group of birational self-maps of the surface is cyclic of order 2. And let me explain to you this involution tau. So you have the equation here. So if I give you x1, x2, and x3, you can solve for x0 and get two solutions in general. And so this involution tau is the one that permutes these two solutions. And if you take a general quartic surface with one singular point, this is the only birational self-map of S. And so we have this restriction homomorphism, and in fact, we can produce explicitly a volume preserving Cremona transformation that induces the tau. So you can check that this is an involution, birational involution of P3 that preserves the hypersurface and induces the involution tau on S. Okay, and because it is also this phi is also an involution, we have this structure, this split exact sequence, and this gives us our main theorem B that says that the birational group of P3 that stabilizes the hypersurface is a semi-direct product of a group G, which would be the kernel of the restriction, and the Z mod 2Z. And this group G, actually, our tools always also allow us to describe this group G. This is what we call a form of GM over the function field of the plane. And concretely, I can tell you exactly this G. If you are interested in explicit mathematics, I can give you an expression for all the elements of this group G. So this G is a complex group. It's a group, but it also has a structure of an algebraic variety. So this is the group G. And just to wrap up, let me just go back to the problem of automorphism of quartic K3 surfaces. So if you're given a quartic K3 surface S, you may be interested in which automorphisms of S are induced by a Cremona transformation of the ambient space. And we would like to describe this homomorphism. And to do so, what we've been doing is exactly looking at the Sarkisov program for the volume preserving version of the Sarkisov program and understanding at each step what restrictions on S it will impose. Okay, so this is what I wanted to tell you, the math that I want to tell you today. So I thank you very much for your attention.
Thank you, Carolina. Are there any questions that the audience would like to pose? You can unmute yourself and ask Carolina.
Yeah, hello. So this is Jaya. So I have a question. Can I go ahead?
Yes, please go ahead, Jaya.
Yes. So actually, Carolina described a morphism from the birational maps of your ambient projective space, which leaves the surface or the hypersurface invariant to out S actually. So instead of this homomorphism, so is there another version of looking at birational maps of P3 leaving an open set of your S actually, of your hypersurface?
Yes,
and,
thank you very, yes,
and
sorry.
The restriction to the BIR of S actually.
Yes, yes, thank you very much for the question. Let me if I put back some slides back, you will see that here I use the birational group of S and not the automorphism group of S. And the reason is the following. If you have in this case, in this specific case, when I have this tau, this birational map is not an automorphism of S because S is singular. But in my last slide here, I have an improvement because I'm taking S to be a smooth hypersurface. So if you have a smooth K3 surface, a smooth quartic hypersurface, then every birational self-map of S is automatically an automorphism. So this is why in this case I could use automorphism. But you are right. If I was considering, as I was previously, possibly singular hypersurfaces or in general other types of hypersurfaces, then I would have to always use the group of birational self-maps of S. So here I'm using something strong about a smooth K3 surface, that every birational self-map extends to an automorphism.
Okay, so here actually when you write the notation omega S, so does it mean that you are leaving only an open set of S fixed? Or,
yeah, well, yes, but then it automatically will leave the whole surface. It will stabilize the whole surface. It does not leave it fixed point-wise. It's just fixed the it induces a birational map of the hypersurface.
Okay, so in general, actually, what can you say? Is it surjective or so actually?
Yes, so we do not, well, this is what I'm working on. So there are examples where it is surjective. So there are examples where it's not surjective. Yeah. So this Ogiso constructed this interesting example where the automorphism group is Z, but no automorphisms except the identity is induced. So the homomorphism would just take everyone to 0. Or to the identity. But there are other examples where the group is super complicated. It could be a free product of cyclic groups, but still every element is induced by a Cremona transformation. So it is not clear yet what the ultimate answer should be. So what we can do, or what I'm learning, like we've been learning to do in many examples, is if you give me the surface S, I can work it out and understand this map and the image of this map. But we do not have yet any general statement that would hold for we do not have a characterization of the image of this map. So this is definitely a very interesting question, but it's at the moment, I think it is still out of reach, but we are working on it.
Just one more question. So actually in the first slide, actually when you describe that for a hypersurface, any automorphism comes from your ambient projective space. So you have a similar result for complete intersections there.
Sorry, here, right, okay.
No, in the first slide, you mentioned that, okay, you look at some hypersurface, smooth hypersurface, for example, in a projective space. So then any automorphism of your hypersurface comes from your ambient projective space. So that map is surjective.
Yes.
So such a result, does it extend to complete intersections as well?
No, I think when you go to complete intersections, things get much more complicated. There's not, I don't think there is a similar statement for, no, I don't think that you can get a similar statement for complete intersections. I don't think so. I don't think, maybe on some very, you can have some very special cases.
Okay, thank you very much.
You're welcome.
Any other questions from the audience? Otherwise, let's thank Carolina for this wonderful talk. I think for people who are not familiar with algebraic geometry, they're also going to get a sense of the kinds of questions that you're working on. So thank you very much for that. And I would now like Carolina to tell us more about the activities that she's been doing. So she has a special set of slides that she has prepared to talk about the activities that she has been doing as vice president of
yes, so here, can you see it now?
Chair. Yes, we can.
Okay, so I talked about symmetries in algebraic geometry. Now I'm going to talk about gender asymmetries in mathematics. So this is basically, this is just a set of slides to tell you more or less about my activities related to women in mathematics. And I should say that well, I'm currently the vice chair of the IMU Committee for Women in Mathematics, and I'm very happy to be working with Neela Nataraj as my Indian friend and colleague from the Committee for Women in Mathematics. And so actually maybe I should have put this slide in the beginning. So this is just to tell you where I work. I'm at INPA in Rio de Janeiro. This is the logo of the institute. I put a map so that you can find me. And this is the entrance of the institute. And I will show you a more lively picture of the entrance at the last slide. So as I said, I'm currently vice chair of the Committee for Women in Mathematics. I invite you, I'm sure many of you are aware of the activities. We've been, the Indian Women and Mathematics has been a very good partner of CWM over the years. But if you are interested, you can see the website of the committee to see some of our activities. But let me just tell you a brief history of the Committee for Women in Mathematics. It was created in 2015 after the ICM 2014 in Seoul. So this is a very impressive picture of the opening ceremony of the ICM 2014 in Seoul. We see at the center of the picture three wonderful and powerful women. So we see the ex-president of South Korea. We see Maryam Mirzakhani, who was the first woman to receive the Fields Medal, and Ingrid Daubschys, which was the first female president of the IMU, the International Mathematical Union. And so I think this gives us a lot of force to start the committee and and start developing many activities, but we have to be very aware that in history we go back and then we go forth and then we take some steps back. So let me show you a picture of the opening ceremony of ICM 2018, 4 years later. And then here you see that there in this picture there are mostly men. There is one woman in this picture, but she's not a mathematician. She's representing the Brazilian Development Bank, which was the main sponsor of the event. So she's the only non-mathematician in this picture and also the only woman in this picture. So we see that we take some steps forward, then take some steps back, but we keep working. And in 2018, we organized the first world meeting for women in mathematics. This was a satellite event of the ICM 2018, and this was a very beautiful event. So I met Ridi Shah in this meeting and met women from all over the world. And so this you've probably seen this movie, The Journeys of Women in Mathematics, that was premiered in the WM Square, and Nila also takes part of this beautiful movie. So if you haven't seen it, I just highly recommend it. Also, during the WM Square, we organized this exhibition, a memorial to Mariam Mirzahani, and since then this exhibition was shown in many parts of the world. And something very important also happened in WM Square, which was the beginning, the birth of the initiative May 12, celebrating women in mathematics. So the representatives of the Women's Committee of the Iranian Mathematical Society made a proposition during the WM Square that we should celebrate May 12 as this would be a celebration day for women in mathematics. So this was the picture of the vote. And so the initiative was approved, and now it is an international initiative that is organized by many international organizations for women in mathematics, including the Indian Women in Mathematics organization. So we are very happy to work together on the May 12 initiative. So May 12 is coming soon. So I encourage you to celebrate it. And so this is the first May 12 celebration in 2019. So we had 109 events all over the world. In 2020, because of the pandemic, most events were remote, and I guess the same will be true for 2021. And here are some future plans for the Committee for Women in Mathematics. So we are already thinking of the organization of the second World Meeting for Women in Mathematics in St. Petersburg. So this is going to be a satellite activity of ICM 2022. We are also planning some CWM ambassadors regional meetings. So we have a program of CWM ambassadors with women connecting CWM to the activities in their countries. We are planning a new exhibition for the WM Square 2. We currently have twice a year a CWM newsletter, which you can find in our webpage with lots of information. And soon, well, as I said, we will have the May 12 celebration. So this is some activities of the Committee for Women in Mathematics. And also, I've been also involved with organizing many events in Brazil. So this was in 2019, the first Brazilian meeting of women in mathematics that I organized at IMPA. And then you can see the picture of the entrance as I promised you. So a much more lively and colorful picture. So I just would like to finish by showing you this picture and the picture of our meeting with many women mathematicians from Brazil. Thank you very much.
Thank you so much, Carolina. Would you like to tell our audience a little bit about your own journey in coming to mathematics? And did you? I know you. It says that you liked it at school, but how did you end up being, coming to mathematics and taking that up as your career? And did you face any problems?
Okay, so one thing is that I think it's important to say is that my mother herself is an engineer. So I had a role model at home. So my mother, I remember when I would get a good grade in mathematics in school, my grandmother would tell me, "Oh, you're just like your mother. You're good in math like your mother." So for me, mathematics was a natural place to be. My mother was very good in math. And actually, when I first thought about doing engineering, following her steps, but I was also very curious about other STEM areas. So when I entered university, I started to take courses in physics and in engineering and in mathematics. And as you mentioned in the introduction, when I took my first serious mathematical class, then I knew that was my path. So for me, it was very clear. There was no doubt at that point. And then I did my PhD in the US. That was actually a very difficult moment for me because it was a very different environment. It was very competitive, and I felt that I had a feeling of non-belonging that was very hard to deal with. And I think what helped me a lot was exactly the fact that I had a group of female mathematicians, colleagues, and we were very close. We would get together in the weekends to hike. We would organize brunch. Would have breakfast together. We would go out to sports together. And I think having this group of other female mathematicians helped me feel that place was also mine. So I think this is I can't emphasize more the importance of being connected in network, because being in a very masculine environment can make us feel that we don't belong to that place. And so I think that having this network of women gives a feeling that yes, we can be here, and this is also our place to be. And then but I have to say that at that time I did not think so much about these issues. I think I naturalized very much the fact that mathematics was mostly a masculine environment. Only more recently I started to think about this and think about the effects that it had on me and on my research, and I started to look at what happened to other women and noticed that many women were actually leaving science because of a hostile environment. And so this is where reflection. And I think that a lot of it is because I had a role model at home. I think things were a bit easier for me. I had this. I brought the confidence, from very young. So I think this is for other women that do not have that may be much harder.
Are you still the only woman in IMPA?
No, I'm not anymore. I have now a very nice colleague, Luna Lomonaco. She joined us at IMPA in the end of 2019. So now we are two, And it's great to have her around. She's a great researcher, a great friend. So it's wonderful.
Thank you so much, Carolina. I don't know whether, Riddhi, we can open out some questions to the audience, or...
Yeah, sure, no problem. This is the last talk, and we would not have Carolina with us so easily. Well, maybe yes, but this is the opportunity for everybody to ask questions to Carolina and gain from her experience, non-math, math, whatever you want, career, anybody.
I want to read out Professor Ajit Iqbal Singh's comment.
Yeah, sure, go ahead.
A senior, one of our senior most women professors, and she's been an inspiration to all of us. And she says, Carolina, wonderful talk and interaction, Carolina, not just a corollary to mom's talent, but a significant theorem herself.
Thank you very much.
May I ask a question, Geeta?
Yeah, of course, Padmavati, please go ahead.
Hello, Carolina. I'm Padmavati here.
Hello.
I wanted to know, how was it in your school days when you studied? Did you have a comparison with the boys with respect to ability in mathematics, or how is it?
Well, when I was in high school, I have very good math teachers. So this was wonderful. Both female and male math teachers. And I remember that I liked it very much, and I studied very much. And I was the best one in class. I was best than the boys in my school. But I did not know this, but until in middle school, they had one teacher that he used to, I don't know if this is good or not, but he used to rank the students according to the grades. And then in the end of each term, he would give a list, and the first prize, the first one in the list would get a cake. And this is how I found out that I was doing better than the boys at that time, because of the cake that I got. But I'm not sure if this is, I don't know if this is a good thing to do. I'm not sure. I don't, I think that competition, for some people, competition can be very good. I think that makes them want to excel, and then that for them, it's a great incentive. But I myself don't feel so comfortable with competing. So I don't know if this is a good thing or not.
You didn't have any competition, right? So
thank you.
Anyone else who wants to ask a question?
I think Ajit may want to ask. Ajit?
Ajit, I don't know if she's unmuted herself.
No, she hasn't.
She hasn't. Carolina, what about the situation in other institutions in Brazil? I mean, is there a good representation of women in the student body as well as in faculty when it comes to mathematics?
So unfortunately, no. So of course, I think the discrepancy at INPA is very strong. I think we are around 45 researchers and only 2 women. So this is very low. So I think in the university, in other universities, the situation is slightly better, but still, in general, we have a very low representation, and I think it is, as in most parts of the world, when you see as students, undergraduate students, it's close to 50-50. And then when you start the master, you just decrease, and the PhD, and then for in higher research, you see very few. So I think we have a program of grants from the government, individual grants for the government, and among math, I think the women that hold these scholarships are only 10% of the grantees. So this is very low.
I just wanted to know what could be the reason. In India, there are social pressure for women. Also, if there is a financial issue, then they'll say, okay, the boy will study, the girl will not. And also they say, oh, girls shouldn't study too much. They have to anyway get married and cook, and they should not be more educated than the husband. I mean, the
In fact,
boy.
that's why I was asking her about the school.
So, what would it be in Brazil? I mean,
it's not so, unfortunately, it's not so difficult. I mean, of course, there are some subtleties. I think if each culture will have its own singularities, but I think what you said could also applies to Brazil. I think that there is this this bias, this prejudice that women are not good at math, and this is already from the basic school, and in the middle school it's really bad. So in Brazil we have this very important program of Olympiads, that it's not an elite Olympiad program. We developed a country-wise program of Olympiads that goes to more than 99% of the schools in Brazil. They participate in the Olympiads. And then there you can see there are different stages according to the age. And then you see that that the participation of women as they get older, or of girls, I should say, when they start to get older, it starts to decrease, the participation and the success. And by the time that they are teenagers, then they have already been excluded. We don't see them anymore in the Olympiads. So we have to do something very early. So I think it's clear that that there is a cultural problem. Something is excluding women and putting them away from math. And so we are losing so many talents in this way.
You did, those Olympiad children were invited to one of the popular talks in ICM, right? I noticed, and there were a lot more boys than girls. That is true.
Yes, exactly. Yes.
Do you have something like IWM in Brazil, or an equivalent?
Well, not exactly, because we have a network of women in mathematics, and this is the picture that I put in the end. It's one of our pictures, but we do not have an institutional organization. Our network is very informal and sort of organic. So I'm part of, for instance, this event, the first Brazilian meeting of women in mathematics, was organized by a group of around 30 women. It was a very big organization group, and things were done in a very horizontal way. And so that created some networks, and we also have some other networks. So it's a different type of organization. I should say that I think it's a very good thing that it is it's not centered, and it's organic, but at the same time, of course, things take longer to develop in this way.
Yeah.
So there are the pros and the cons, but
so would you be thinking of an association of women in Brazil or something like that eventually? I mean, is that where the network would be headed?
So I don't think so. I think that So I think there are many parallel organizations, and each one has a role. For instance, recently we have now a gender committee of the Brazilian Mathematical Society, which I'm not part of. I have some very good friends working there, but they work together with other groups. So we don't have a centralized organization. Maybe we will have, but for the moment, I think
Yeah. No. I didn't
Also
mean centralized, as in like we are funded by the government. But what I was thinking more along is European Women in Mathematics, or the Association of Women in Mathematics, like the Americans have, where it's something that you join and become a member of, and then they do things. I was thinking more along those lines, because you seem to be starting in that manner when you have this, loose network and organization which is already there.
Yes, it may be possible. So there are people. Some of the members of our network are thinking of having something like this. But this is, I think, also because of the pandemics, things got a bit stuck. But there are some plans of doing. Something. At least having a focal point for the efforts, which would be something important.
May I ask another question, please?
Sure, Padmavati, go ahead.
I want to know whether you did the mathematics in Portuguese when you were in school.
Yes, mostly in Portuguese. Of course, some of the textbooks that we chose to read were in English, but most of it in my undergraduate, most of it was in Portuguese.
So how easy do you think the students feel when they have to, study in English? So for
some of them it's hard. So what I try to tell my students when they enter the master, so we have a master in PhD program at IMPA. So I already tell them to start learning. If they don't, to start learning English and reading articles in English, because in the end, this is the working language. The English is the working language. So for some of them,
is it taught actually?
Sorry?
When is it taught? English?
English. Well, people should have at school, but that will depend. That the quality varies a lot. So some people come already with knowing a very solid English. Some people don't know English at all, and then they have to learn it together with the math. So that is an extra challenge. But in the end,
I have more mathematicians doing well in Brazil if the medium was Portuguese.
Well, so I usually, when I teach my courses at IMPA, I teach in Portuguese. Some other colleagues, they prefer to teach in English, and I think this is exactly because of that, because I know that still some students are still not fluent, and so I prefer that they use their energy to understand the math. But on the other hand, the textbooks for instance, when I teach a PhD class, of course, the textbooks are in English. So in this way, they start to learn some. But I don't know, some other colleagues think that it's better to teach already in English. So I think that it's a personal choice also.
Yeah, here we have many languages, and a lot of people do schooling in their own mother tongue, and then they switch over. And in fact, I feel maths is much easier to switch over from, your language to English rather than other descriptive subjects, which takes much longer to switch over, I think. I don't know.
Mm-hmm. Yes, I agree. Yes.
So let me mention, Carolina, that IWM is very grateful to CWM because, we do get funding from government and all, but there are certain things where government funding cannot be used, like our regional programs and all, which have been very useful, that what you have, because government funding is very good. They promise everything, but there are certain caveats where we couldn't use, and those we thought were very important. And we have been very lucky to and grateful for this funding from CWM, which has been really useful. Thank you very much.
Okay, so Aisha, I also would like to say that I think it's very good to have the partnership with IWM. So it's so we've have a history of partnerships, and I think IWM is doing a great job. So so the funding is well deserved.
Thank you.
Any other questions or comments that people want to make? Otherwise, Riddhi, I'll hand over to you, and then we can close for the day.
Yeah. Okay. Yeah. Thank you, Carolina, for such a wonderful talk. It was very inspiring for the presentation about CWM. More participants will get to know about this, and also your personal journey, and also agreeing to answer questions early in the morning for you. And we are really grateful, and we are really lucky to have you in this conference with such a vast experience about activity related to women in mathematics. And we hope that you will join tomorrow evening for our closing ceremony, where we are going to release our logo. So I hope you can make it. It's around same time, 4:45 tomorrow evening, so 15 minutes later than your talk today. Thank you, Geeta, for managing and chairing the session so well as always. And I must mention to Carolina that all the people in IWM, every single one of them works so hard and on different things. You can rely on the whole team. Somebody takes charge of regional workshops, somebody takes charge of winter school, somebody takes charge of annual conference, and many things. They do it all together. The team works very well together. I'm really happy. I think somebody wants to talk. Is it Rupal? Do you want to talk? I see her photo. Maybe it's just a mistake. So with that, we meet tomorrow at 9 a.m. It's a talk by Pallavi Dani from Louisiana State University. I hope everybody will join a little bit earlier than 9 so that we can all be there for the tomorrow's session. And with great reluctance, we take your leave today, and see you tomorrow at 9 a.m.
Thank you, Riddhi. Thank you, Carolina.
Yeah. Thanks, Riddhi. Thanks, Neela. Thanks, Carolina. And bye, everybody. Hope to see you all tomorrow.
Yeah. Bye.
Bye.
Bye bye, everyone. See you tomorrow.
Bye. Bye.